Today, I'm going to review rotations. Before we do that, let's do a brief review of translations.
Translation describes one way a geometric shape can move on a coordinate plane. When you translate a shape, it's like you make an exact copy of it and slide the copy to another spot. The shape stays the same. Here's how it works. Say we want to move this triangle to another location on a coordinate plane. First, we name the ordered pair for each of the shape's vertices. Then, to show where the shape is moving, we can use a mapping notation like show the translation. If we move +4 on the x-axis, then we know to move the shape 4 to the right. And if we use -2 on the y-axis, then we know to move the shape 2 down on the coordinate plane. Now we know which direction to slide the shape. Notice that the move shape is congruent to the original, which means their corresponding angles and sides are the same. We use these little symbols to show what we've done to create this translation. So there you have it. When a geometric shape is moved on a coordinate plane, it's called translation.
So that is translations. Today we're going to get into rotations. A rotation is often referred to as a turn in a plane. A rotation is a type of rigid transformation, therefore meaning that the size of the shape does not change, the length of the sides does not change, the angle measured does not change, the type of shape it is does not change. Therefore, it's a rigid rotation. Every point of the pre-image is moved by an angle of rotation about the center of rotation to create an image. I'll show a video that explains this a little bit further.
Math Shorts. Rotation describes how an object turns around a point. It's used to describe the movement of geometric shapes. For example, if you tack up only one corner of a rectangular sign, what's going to happen? The sign swings down. It has a rotation around the tack, but geometrically, it's the same shape. Rotation is really common. The triangles that make up spokes on this bike wheel are rotating around the center axle. Mathematicians use rotation to describe shapes on a coordinate plane too. Check out this triangle. In mathematical language, we'd show it like this, which describes the points of the triangle's vertices based on where they're located on the coordinate plane. To rotate an object, you first need to choose the center of rotation. This is the point that you'll rotate the object around. To make it easy, we'll choose point 0, 0, or the origin, on this coordinate plane. When we rotate the shape, we need to keep the shape exactly the same distance, or equidistant, from the center of rotation all the way around. If we rotate the triangle 1/4 turn around the point of origin, counterclockwise, keeping the point of rotation exactly the same, then the triangle moves to a different place on the coordinate plane. The triangle shape stays the same, but the triangle has rotated, and the points used to describe the triangle have also changed. To show that a triangle has rotated, we use a little symbol like this. So now we have turned a geometric shape around a point. That's what rotation means. We can use it to move shapes and describe their movement.
That is an overview of rotations. Today we're going to get a little bit further. But first, let's look at this. All the points are rotated in a given direction. We can either have a clockwise rotation or a counterclockwise rotation. Clockwise is the way we normally read the clock, 1, 2, 3, 4, 5, 6, and so on. Counterclockwise goes the other way around, 12, 11, 10, 9, 8, 7, etc. The rotation occurs around a center of rotation. When angles of rotation are counterclockwise, for the center of rotation, the angle is positive. So positive 90 degrees, positive 180, or positive 270. If the figure is rotated clockwise, on the other hand, the angle of rotation is negative. So a rotation about negative 90 degrees, negative 180, or negative 270. Counterclockwise, positive, clockwise, negative. Rotations require a center of rotation and an angle of rotations. Rotations are a type of rigid transformation, so therefore the angle measures are preserved and the side measures are preserved. We represent rotations like this. Rotations R, which represents rotation, O, which represents about the origin, and then an angle. This angle will tell us the angle of rotation. We have different types of rules for rotation. We're going to go ahead and dive into these different rules. Let me share my screen. Here are our different rotation rules. We're going to look at a rotation for a counterclockwise 90-degree rotation, a rotation for a counterclockwise 180-degree rotation, and a rotation for a counterclockwise 270-degree rotation. Whenever we have a counterclockwise 90-degree rotation, we negate the y coordinate and then switch the x and y. Whenever we have a counterclockwise 100-degree rotation, we just simply negate the x and y. And whenever we have a rotation counterclockwise 270 degrees, we negate the x coordinate and then switch the x and y. Let's look at some examples. Say here I have a positive 90-degree rotation, so a counterclockwise 90-degree rotation. Well, I know what I need to do first is negate y, and then switch x and y. So what I want to do is identify the points on my original figure, my pre-image. Let me go ahead and write these over here. What I want to do is see where these different vertices map after this specific rotation. So the first thing I want to do is to negate my y. Lastly, I'm going to switch x and y. Here I am. Now I can go ahead and map my resulting image. Oops. Right here. Okay. And by doing so, I can see where my square maps after that specific type of rotation. Now let's say we take the same image, but now we do a rotation about the origin, counterclockwise 180 degrees. Well, we know here that all we need to do is negate the x and y. So changing the sign. So I'm going to do that to all the coordinates. And now I can go ahead and map this. And by doing so, I can see where my resulting image is after a rotation of 180 degrees. Lastly, we're going to look at a rotation counterclockwise 270 degrees. We know when we have it rotation of 270 degrees, we negate the x and then switch x and y. So, first thing I'm going to do is negate x and then switch x and y. And then I can go ahead and see where this maps to. And by doing so, I can see where my new square maps to. Lastly, what about if I have a rotation about the origin 360 degrees? Well, we haven't looked at a rule for this, but if you turn something 360 degrees around, it basically just maps back to itself. So the original coordinates will map back to themselves. And so therefore, our resulting square will be located right here again. So that's how we can use the different rules to go ahead and find where our pre-image maps to after a specific type of rotation. Now let's look at this one. Now we're asked to find the pre-image. What is the pre-image of the figure if the rule that created this image, the resulting image, is r about the origin negative 90 degrees? Well, because we have a negative 90 degrees, we know we need to move clockwise. However, we weren't originally given any rule for a rotation clockwise 90 degrees, only counterclockwise. Well, whenever you have a clockwise rotation, all you have to do is do the opposite of your rule, work backwards. So we will apply the rules backwards. So originally we would negate y and then switch x and y. But when we're doing a clockwise rotation of 90 degrees, we first negate and then switch. Okay, but of course we are trying to find the pre-image, so you would keep the original way. So negate y and then switch x and y. Because we know when we're looking for the pre-image, we need to do the opposite of what we originally did. What we originally did and what we just identified is we originally switched x and y and then negated y. That's how we originally did a negative 90 degree rotation. However, because we're looking for the pre-image, we want to work backwards. So that means doing the opposite. So let me go ahead and negate y. And then now switch x and y. There we go. And then if I wanted to map that, q is at negative 2 and 5. R is at negative 2, negative 1. S is at negative 4 and 2. And so this represents where our pre-image was located. Okay. So we learned that a rotation is a type of rigid transformation. The angle of rotation is counterclockwise when positive and clockwise when negative. Orientation is not preserved other than when we have a rotation about 360 degrees. And then we had specific rules for rotating about the origin. The last thing that we learned is that whenever we have a negative rotation, for example, negative 90, negative 180, and negative 70, what we want to do is apply these different rules backwards. So the rule for negative 90 is to first switch x and y, and then negate y. The rules for negative 180 stays to negate x and y, because there's no opposite of that. This one, switch x and y, and then negate x. Those are the different rules that we have for rotation. I hope this was helpful. If you have any questions, please do not hesitate to ask me. I am here to help. Bye, guys.